Do the others know that we have talked about it? That's great. Okay. All right. Anyway, so this question is asking for the CO stretching frequency, not stretching frequency, CO stretching vibration energy, okay, the transition energy. And then if we switch to, give me a second, to my notebook, okay. We all knew, because I mean, most of you said that we already talked about this. We already solved for this, right? So we are given the wave number for the CO stretching frequency, which is 1000 per centimeters. With that, we converted that to meters, which is going to be 10 to the power of minus 5 meters. And then we plug and chuck that number into this equation to get the energy of that transition or energy of that photon, which is 1.98 times to the power of minus 20 joules. So this is what we did on last Thursday. Okay. But I mean, I'm asking you to calculate the kilojoules per mole as well. This is basically converting the units to kilojoules per mole. I know, I mean, that's the only thing you have to do there. Yeah. And which is basically multiplying the energy of one photon, which is this guy, by the energy by 1 mole of photon. In 1 mole of photons, we have 6.022 times 10 to the power of 23 photons. Okay, so if you multiply 2 by, which is 1.98 is 2, right? Basically 2 times 6.022 is around 12, right? And then 12, and if you do the exponents, 10 to the power of minus 20 times 10 to the power of 23, I mean, they will cancel out to be, you know, something around 12, kilojoules per mole. So we have done everything at that point. Not convinced? Okay, we'll do that again. All right, let's do this. Okay. Now, here's the energy of one photon. Take that, okay, which is around 2. Okay, 1.98 is essentially 2 times 10 to the power of minus 20 joules multiplied by the Avogadro's number, which is 6.022 times 10 to the power of 23, which is the number of photons in a mole, per mole. And then divide this by 1000, which is 10 to the power of 3. That's because that's how many joules we have in a kilojoule. Okay. And now we see the joules cancel out. And then 10 to the power of 3 cancels out with 10 to the power of 23. So we're going to get 10 to the power of 20 here. 10 to the power of 20 cancels out with 10 to the power of minus 20. And then we essentially multiplying 2 by 6, which is 12 kilojoules per mole. Done. Okay, that's the conversion between joules per photon and kilojoules per mole. All right. What questions, concerns, comments do we have at the moment? Just a reminder, okay? Now, the idea is very simple. Whenever you are asked to calculate the energy of a transition or energy of a photon, that's the equation we're going to use. Energy is equal to Planck's constant times the speed of light divided by the wavelength. That's it. Okay, that gives you the energy of a photon. And then if you ask to calculate, convert that to kilojoules per mole, then multiply that by the Avogadro's number and divide by 1000. That's it. That will give you the kilojoules per mole. Okay. Now, this type of calculation, okay, where you are given the wave number and asked to calculate the energy of the transition, is the most complicated version of this use of this equation. Okay, this is as complicated things can get when it comes to these calculations. But if you can do this, which I mean, you know, you'll be fine. Again, things are very simple here, right? The wave number is 1 over wavelength. Right? Whenever you are given the wave number, first convert that to the wavelength. How do we do that? We know 1 over wavelength is 10 to the power of 3 per centimeters in our question. Therefore, the wavelength is 1 over that, 1 over 10 to the power of 3. That's in centimeters now. But we want to convert that to meters, okay? Because we always convert things to meters because otherwise we cannot use them in our equation. And therefore, I'm going to multiply this by 10 to the power of minus 2 because that's how many meters we have in a centimeter. And then we just plug that value in this equation and chuck it in our calculator. And that's it. We're done. That's all we had to do there. All right, please. What questions, concerns, comments do we have at the moment? Anything? Any questions, concerns, comments? Anybody wants me to reopen the question now? Yes, okay, thank you. All right, I just want you to speak. That's okay. All right. Here we go. I'll give you 30 seconds or something like that. Talk with each other and make sure you understand this. If you have any questions, ask. Ask from your neighbor, ask from the learning assistants, ask from me. All right, that's it. Anything. All right. That came up.
Hope that's gonna happen.
Now, do not get tricked by this, okay? So you have 1.98, which is the exact number you got from the calculation, times 10 to the power of minus 18. But we get 10 to the power of minus 20, not 18.
Sadly.
Okay? Even though this is 1.98 matches exactly with your calculated number, this number over here is 100 times off, okay, compared to the correct value. On the other hand, if you go to option A over here, okay, we have 2 times 10 to the power of minus 20, and this value is only off by 0.02. Okay, so whenever you have to select between the options, go with the closest one. The closest one to our correct answer here is option A, not option A. Option A is 100 times incorrect compared to the correct value. All right. Any questions, concerns, comments at the moment? Anything? Okay. Now, with that, all right, this is just a reminder about what we have done already. But anyway, I mean, these are the, okay, again, I mean, I'll have some practice problems like this in the discussion worksheets as well. Okay. So with that, I want to go back to the beginning. So we started unit 2, module 2 by talking about the covalent bond, right? And then we talked about how covalent bond formation is stabilizing. Why? It decreases both the kinetic energy, give me a second, and the potential energy. Okay. As a result of that, it decreases the total energy. Any process that decreases the total energy is a stabilizing event, stabilizing process. The bond formation is stabilizing. Why? It decreases the total energy. Okay. And then we talked about why it decreases the total energy as well. Due to delocalization of the bonding electrons between two atoms, the electrons have more space to move around. Therefore, they slow down. Therefore, the kinetic energy decreases. And also, the electron repulsions between the bonding and the non-bonding electrons decrease. Therefore, the potential energy decrease as well. And there are other reasons why the potential energy decrease, but we at least talked about one or two of them here. Okay, and then I posted this slide with all the reasons together with the class notes from last week. All right. Anyway, so now we have talked up to this point. We know due to bond formation, energy of the system decreases, and that's why the bonds form. Not because they want to be like a noble gas, they want to form a bond. They do not have wants, needs, or greed. Okay, those are atoms. Okay, those are our feelings. The atoms don't have those feelings. They make bonds because it is decreasing the energy, total energy. That's the only reason. Not because they want it. We want it. They don't. All right. Anyway, so please keep that in mind when we explain things. We're not going to use terms like want, need, greed. Okay. No emotions. All right. We're going to be like ChatGPT when you answer free response questions. All right. Anyway, now there's something else I want to do here before I move on about the bond formation, because that's a homework question. So that is this. All right. I want you to pay attention to the second simulator over here. I have the internal potential energy or the potential energy on the y-axis and the distance between the atoms over here. Now, let's think about a bond between two hydrogen atoms. All right. So when the atoms are far apart, potential energy is set to 0. And then when I bring one atom closer to the other, the potential energy decreases down to a minimum where we have the bond between them. So at this point, which is the minimum, okay, gives us the distance between the two atoms or the bond length of hydrogen-hydrogen bond over here. Okay, and if we try to push these atoms even more close to each other, the potential energy shoots up. Why? There are repulsions. Okay, so now you see that there's a nice curve built up over here. Now, here's what I want you to appreciate. Okay, in this curve, give me a second. Right, 2 points. Okay, actually, the first point is the minimum over here. Okay, so the distance between the atoms at the minimum point, which is given by the x-axis over here, gives you the bond length. This is the bond length of the bond. Okay. The minimum occurs at the optimum distance between the two atoms. We have the bond, and that gives you the bond length. Okay. And then the other thing is, how strong is our bond? Now, again, when it comes to the strength of the bond, we are talking about attractive interactions between the atoms here. Now, we know the relationship between the attractive interaction strength and the potential energy, right? What's the mantra again? Anybody? What's the mantra between the potential energy and the strength of attractive interactions, please? Somebody should know it. I know you know it. And you know it. The stronger the attractive interactions, thank you, the lower the potential energy. Yeah? So now the dip or the minimum of this curve gives us, okay, so the minimum occurs at the lowest potential energy. All right. This gives us an idea about the strength of the bond or the bond strength. Bond strength. Okay. So lower the minimum is, stronger the bond is. Stronger the bond. The lower the minimum, the stronger the bond. That's the idea. All right. Now, here's how we're going to use it. Here's how the questions are posed in the homework as well. Okay. We are not going to use just one curve. We're going to use we're going to compare like at least two curves. Okay. Let me get rid of my doodling first. Okay. Now I'm going to change this to a bond between, right now we have a hydrogen-hydrogen bond. Let's make a hydrogen-oxygen bond. Here we go. Okay. Now, if I do the same thing over here, so now this is when they're far apart, and then when they come close to each other, okay, here we go. I'm going to, do this a couple of times, or maybe more than a couple of times, until I get a smooth curve. Okay. I think this is good enough. Now I'm going to label so that we know what we're looking at. So here's my OH bond curve. And then here's my HH bond curve. Okay. On your whiteboards, I want you to tell me which bond is longer and which bond is stronger. Go ahead. So on your whiteboard, write longer bond, okay, this one, and the stronger bond, the other one. All right. Can I see your whiteboards, please? I want to see your whiteboards. Okay. Longer is the OH bond, and then stronger is, I like it. Okay. Stronger is the HH bond. Thank you. Okay. Almost everybody who wrote something on the whiteboard wrote that. And, there are some people who wrote that in different way. OH bond is longer and weaker as well. Okay. That's another way of comparing them, saying the same thing, which is great. Okay. Now, just to make sure everybody's on the same page, we know HH bond is stronger than the OH bond. Why? The minimum occurs at a lower potential energy for HH, meaning it has to be a stronger bond. Okay. And then the OH bond is longer than the HH bond. Why? The OH bond minimum occurs at a longer distance, which is over here for OH. Okay. HH is over here. Okay. Therefore, the bond length of OH must be greater than that of HH. That's it. Anyway, do we have any questions, concerns, comments at the moment? Anything? Bless you. There is a top hat homework question on the exact same thing. Now we know how to do it. Okay. Any questions, concerns, comments? All right. Now, with that, what I want to do is I want to talk a little bit about the bond. First of all, let me zoom out. I zoom in a lot. All right, this is better. All right. Now, remember in a bond, how many atoms do we have in a bond? Thank you, two, right? We have two atoms in the bond. Okay. That's what that's what a bond is. Two two atoms connected to each other. Okay. Now, what keeps those two atoms connected to each other? If somebody asks you what keeps it connected to each other, what is holding them together? What would you say? Thank you. The bonding electrons. Okay. The bonding electrons hold the atoms closer to each other in the bond. Okay. Now, here's the thing about the bonding electrons. Okay. The thing is, they are electrons. Okay. You know what electrons do, right? They move all the time. Okay. It doesn't matter whether they are bonding electrons. Okay. They don't care about their label. All right. They're gonna move. Okay. When they move, the bond also moves. The bond length also changes. Okay. So as a result of that, for any given bond, all right, that bond is not going to be a static bond. It's going to be a dynamic bond, meaning the bond length changes around an equilibrium value, which is going to be determined by the minimum on that curve. Okay. Around that value, that bond always, go like that. What kind of a movement is that? What do we call this movement? Okay, this is one atom and this is the other atom. If it goes like this, what kind of a movement is that? Anybody? Come there again? Yeah, thank you. It's a vibration, a stretching vibration. Okay, whatever. Okay, it's a vibration. Now, if something vibrates, we can define what we call a vibration frequency. Okay, so let's talk about the vibration frequency. So the vibration frequency of a bond, let me see if I can, where is my top hat? There you go. Okay, so let's do it like this. In my notebook, it's better. Okay, so the vibration frequency of a bond, okay, has a special Greek letter. Okay, so you know what? It's the same Greek letter for frequency, which is nu. Okay, but just to distinguish this from other frequencies, let's call it nu VIB, VIB, subscript VIB for vibration frequency. Okay, it turns out vibration frequency of a bond depends on two things. All right, so vibration frequency depends on the bond strength. Stronger the bond, greater the vibration frequency. Okay, and then it also depends on the masses of the atoms involved. Let's write that. Masses of the atoms involved. Right? Now, in physics, I mean, you're gonna use the you're gonna make the bond analogous to a spring. And then, you talk about the same thing, okay, something like this. I think it goes like, this is equal to the spring constant K divided by the reduced mass, okay, the square root of that, 1 over 2 pi or something like that. Okay, maybe you have seen that. Don't worry about it. I'm not going to play with that, okay? It's the same idea though, okay? The spring constant is like the bond strength, which is a function of the bond strength. And then the reduced mass, this is mu, is for the reduced mass. It's going to depend on the masses of the atoms involved. But I'm not going to make you calculate anything with that, okay? Only thing that I want you to know is, I want you to appreciate is, the vibration frequency depends on the bond strength and the masses of the atoms involved. That's it. That's all I want you to know. Now, this has some good implications actually, okay? So any given bond has its unique bond strength, and then if that doesn't cut it, the masses involved or the masses of the atoms involved will be unique to that bond. Okay. As a result of that, the vibration frequency of a bond is a differentiating characteristic to any given bond. Okay. In other words, we can use the vibration frequency of a bond to identify it. Okay, and that's it. That's exactly what we're going to do. From here on out until the end of today. Okay, we're going to use the vibration frequencies to identify the bonds. Now, we talked about this the other day. Vibrational motion of molecules is, are induced by what radiation? Well, everybody, one more time. Yeah, vibrational motion of molecules, okay, is induced by what radiation? Thank you, infrared radiation. Okay, therefore, what we're going to do is we are going to be using infrared spectroscopy to identify the bonds. Okay, this is how it goes. Let me actually use the slideshow now, which is better now. Okay, so you know that bonds have different vibrational modes, vibration states. Okay, what we can do is we can use infrared radiation to induce transitions, vibrational transitions. Okay, so the idea is the vibrational states, vibrational energy states are quantized just like electronic energy states. Okay, and that energy gaps fall within the infrared radiation energies. Okay, as a result of that, when we expose the molecules to infrared radiation, we can induce vibrational transitions in the molecules. That's the idea. Okay. By the way, I mean, do not get bogged down by this. Okay. The idea is we are using infrared radiation. Why? Because infrared radiation induces the vibrational motions in the molecule. That's it. That's all. That's the take-home message of this entire slide. Okay. Now, any questions so far? Anything? All right. Now, with that, this is what I want you to know. Okay. Here's an example infrared spectrum that we'll be using in this class. Okay. Now, you should notice two things here. Okay. One, this is still absorption spectroscopy. Okay. In which mode? There are two modes for absorption spectroscopy. Okay. Which mode is this? Thank you. I heard that. Transmittance mode, right? So it's not like the absorption spectra you collected in the lab where you have the like nice peaks. We have the upside down peaks. In other words, we are collecting, or not we, the infrared spectroscopists are collecting data in the transmittance mode. Number one. Okay, they are weird. Okay, we just need to roll with them, right? And also the x-axis. All right. X-axis is not wavelength. What is it? You know it. Thank you. It's wave numbers. Where is it? Can I say it? There you go. Okay. The x-axis is wave numbers. It could have easily been the wavelength, but they have chosen to go with the wave number instead. No, that's the way it is. Scientists are weird. All right. Anyway, do we have any questions so far? Now, here's what is going to happen. Whenever I give you an IR spectrum, okay, I'm going to tell you what bonds we have based on that IR spectrum every time, okay? As opposed to your organic chemistry class, which you'll be taking like in about two semesters, okay? You will have to remember the wave numbers associated with, different vibrations or different bonds. You don't have to do that here. I'm going to tell you what bonds we have, okay? And then this is the important thing that I want you to make a note of, okay? Infrared spectrum tells us, please make a note, okay? Infrared spectrum tells us, okay, what types of bonds we have in a molecule, period. Okay? Infrared spectrum tells us what types of bonds we have in a molecule, and that's it. Or 5 seconds. We have more than 90% answers now. All right. That should be enough time for that question. Anyway, so one more time. Can somebody tell me what I asked you to write just before this question on your notes? What did you write? Annie, what did you write? Period. That's it. Did I say that it's going to tell you how many bonds we're going to have? No, it's not going to tell you how many. Okay. It just tells you what types of bonds we have, and that's it. All right. So please make sure that you understand that. Let's see how many of you paid attention to what we just wrote in our notebooks. Here we go. Look at that. Look at that. All right. Now, the correct answer is, okay, we don't know. Okay. For all we know, that particular molecule have at least one CH bond. That's all we know. It has at least one CH bond. But how many? We don't know that. Okay. Not from IR spectroscopy. Okay. Why? Because IR spectrum only tells us what types of bonds we have in the molecule, and that's it. All right. That's nice. All right. What questions, concerns, comments do we have? Yeah, I need to open this question. I know that. All right. By the way, I'm gonna, I'm opening all these questions after class for 24 hours, right? Okay. I mean, I open this now as well. All right. So with that, let's do another one. Do we have any questions before we move to the next question? No. Okay. Here we go. All right. And oh, look at that. Okay. And here are our responses. Okay. Most of us said CO stretching, and then that's the correct answer as well. Okay. Now, how do we wrap our mind around this? Okay. Now, let's do this in my notebook one more time. All right. Here's my other pen. Oh, here you go. Now, here's how we look at things here. Okay. So we know energy of a photon is equal to hc over lambda. So hc times 1 over lambda. Okay, hc over lambda is hc times 1 over lambda. It's the same thing, right? So what this tells us is this energy is directly proportional to 1 over lambda, which is the wave number. Okay. In other words, higher the wave number, higher the energy. Okay. So now we go, so yeah, anyway, now we go back to our question over here. Okay. We see that CO stretching has the lowest wave number. Therefore, that transition should be associated with the lowest energy photon, okay, or the lowest energy. And then on the other hand, CO stretching has the highest wave number. Therefore, that transition should involve the highest energy photon out of these transitions. Okay, and that's why CO stretching is the correct answer here, because it has the lowest wave number. Why? The wave number and the energy are directly proportional to each other, because wave number is 1 over wavelength. All right. What questions, concerns, comments do we have at the moment? Anything? Any questions, concerns, comments? Please, anything? Okay. Anybody wants me to reopen the question? Oh, thank you. Okay. All right. So that is that. And then we already did the next question, which is the calculation of energy question. Okay. So make sure that, yeah, I'll have it open again one more time. But we already talked about this, which is good. But let's move on. Now, let's do some, application with this IR spectroscopy now. Okay. So this is the way we use IR spectroscopy data. We are going to combine IR spectra with mass spectrometry and elemental analysis. Okay. Remember, when we combine mass spectrometry with elemental analysis, we were able to determine the composition of the particle, like, what atoms and how many we have in a particle. Okay. Just by those mass spectrometry and elemental analysis. Now, if we combine that with the IR spectrum, which tells us what types of bonds we have, we can come up with the structure of the molecule or the structure of the particle. Okay. That's the coolest thing about this experimental technique, because we can finally determine the connectivity between the atoms in the molecule. All right. Here's an example. This is not the best example, but that's okay. Here I'm combining mass spectrum with spectrometer with IR spectroscopy unnecessarily, and you will see why in a minute, but that's okay. Let's do it. Go ahead. think I have 80, more than 85, close to 90% answers now. Okay. I'm going to close this question in 5, 4, 3, 2, and 1. All right. So before I look at your answers, let me show you how I think about this. Okay. So first, it's not necessary for this particular question, but first look at the mass spectrum. Okay. The most important information you get from the mass spectrum is the molar mass of the molecule, which is given by which peak? Anybody? Highest peak? No, it's not. Yeah, it's not about the height. Height doesn't matter, right? We talked about this already. Okay. It's about the peak correspond to the highest mass. That gives you the molar mass of the entire compound, which is like 32 over here. Right. Now, it doesn't matter in this case because all of these options have the same number and types of atoms. Okay. Therefore, they should all have the same molar mass. For that reason, it doesn't matter in this case. But usually, you're going to have molecules, options with different molar masses. Okay. For those questions, that mass spectrum should matter. Anyway, let's just point out. Now, here's the thing to remember. Okay. If a bond is not there in the IR spectrum, it cannot be in your molecule and vice versa. Okay. If you have a bond in your molecule, that should show up in your IR spectrum. If it is not there, that bond is not there to begin with. All right. So let's try this. So let's go over them one by one. Now in option 1, okay, we see that we have OH, CH, and CO bonds. Okay, those are the only bonds we have in this molecule. Okay, but in option 1, we have a C double bond O molecule, C double bond O bond, C double bond O. Yeah, CO double bond. Let's call it CO double bond. Okay, so do we have a CO double bond in the IR spectrum? No, we don't. Okay, therefore option 1 is out. Why? We don't have a C double bond O in the IR spectrum. Therefore, we cannot have that in our molecule, right? And for the same reason, option 2 should be out because we have a C double bond O, which we don't see in the IR spectrum. Therefore, this is out. And then option 3, what can you tell me about option 3? Is it correct? What's wrong with option 3? Everybody, I didn't hear you. What's wrong with option 3? Thank you. C double bond H, right? C double bond H, not there in the IR spectrum. In fact, you can never have hydrogen with more than one bond, at least for our class, okay? Until you take an advanced inorganic chemistry class where you have like bridging hydrogens, okay, and stuff like that, which you don't in 151, okay, or you are from Tempe, okay, hydrogen can always form only one bond, okay? It cannot form more than one bond. Please remember that, okay? So anyway, so option 3 is out. Why? We do not have C double bond H bonds in the IR spectrum. Okay. And that leaves us with option 4 as the correct answer, where we have CH bonds, where we have OH bonds, and then where we have CO bonds. Okay. That matches nicely with our IR spectrum. Therefore, that should be our correct answer. All right. What questions, concerns, comments do we have at the moment? Anything? Any questions, concerns, comments? Okay. Now, we are going to revisit IR spectra and then, determining the bonds in a molecule with IR spectra a little bit later. But for now, this is what I want you to do. Okay. After analyzing thousands of IR spectra, okay, scientists have seen that, let me reopen this question. Scientists have seen that these molecules over here represent the common bonding patterns of elements or common bonding capacities of elements. And what exactly do I mean by common bonding pattern or common bonding capacity? That is how many bonds these elements usually form. For example, let's take carbon in our molecules over there. Okay. In the first molecule, how many bonds do we have for carbon? Everybody. 4 bonds, right? Go to the next molecule. There's another carbon there. How many bonds do we have around that carbon? 4. Go to carbon dioxide. How many bonds do we have around that carbon? 4. Therefore, what is the common bonding capacity of carbon? 4. There you go. Okay, that is called the common bonding pattern or common bonding capacity of that element. Okay, so what I want you to do is I want you to analyze these molecules and determine the common bonding capacities of these elements. Go ahead in your groups. Fluorine 1, oxygen 2, nitrogen 3, phosphorus 3, and sulfur 2. Okay, and these are the correct answers as well. Almost everybody agrees with this. Anyway, now, any questions so far about that? Now, you need to know, okay, let me repeat. Okay, you need to know the common bonding capacities of elements. Okay. Now, does that mean that you want to memorize this? No, I don't think so. Okay, I don't want you to memorize anything here. Okay, I want you to know it. That's the difference. Okay. For example, you know, I know Donald Trump. He doesn't know me, but I know, right? I didn't memorize his name, but I just know him. Just like that, I want you to know this. All right. Now, you know what? Let's do this. Now that we know the bonding capacities, let's try to explain it. Oops, no, not here. Not here. Here we go. All right. Here's a periodic table. I'm going to give you 1 minute in your groups. Okay. I want you to. So, by the way, columns in the periodic table, like this is a column, right? Is also known as a group. Okay. So, this column or this group over here is called the noble gases group. Okay. How many bonds do they usually form? Everybody, how many bonds do the noble gases form? Usually they're from 0, right? Okay, so there's 0 over here. Move on over. Fluorine, chlorine, bromine, iodine, acetylene. How many bonds do they usually form? 1. Move on over. Oxygen, sulfur, selenium. How many bonds? 2. Move on over. Nitrogen, phosphorus. How many bonds? 3. Move on over. Carbon, silicon. How many bonds? 4. That's it. Okay, so just by looking at the position of these elements in the periodic table, we can determine their common bonding capacities, how many bonds they would usually form. That's it. That's all I want you to appreciate over here. All right. Do we have any questions, concerns, comments? Now, I know that some of you are a little bit too advanced. All right. You talked about the valence electrons, like the noble gases, the octet group. We're going to get there, but we're not there yet. We will get there. Okay. But we need about, 1 more lecture to do that. All right. Do we have any questions, concerns, comments? So just by looking at the position of an element in the periodic table, we should be able to determine its bonding capacity in a covalent compound. Okay. And also, do we have any questions at this moment? Anything? I think you might have a question or two, no? Okay. So you can see that there are many other atoms or elements in the periodic table, but I only talked about those elements there, at the top right corner of the periodic table. Is there a reason for that? Anybody? I don't talk about the other ones. I don't care about the other ones here. Why? Why don't I care about them? Anybody? Zoe, any idea? Why don't I care about the other elements? Yeah? Yes, miss. Thank you. That's perfect. Yes. What's the name, miss? One more time? Riley. Yeah. Again, just like Riley said, okay. At the moment, we are interested in the covalent compounds or the molecular compounds, which are made of non-metallic elements. There are only a handful of non-metallic elements in the periodic table, and they are restricted to the top right-hand corner of the periodic table. And that's why I'm only talking about those elements. Okay? Because those are the only non-metallic elements in the periodic table. And then the only thing I would include here is hydrogen. Hydrogen always form 1 bond. Okay. Anyway, do we have any questions, concerns, comments at the moment? Anything? Okay. Now with that, I'm going to clear my doodling. Now what we're going to do next is, you know what? Let's do this problem. Okay. and then we will explain the common bonding capacities. Like, some of you already know how to do that after that. All right. So let's do this problem first. If you have a compound, covalent compound between nitrogen and chlorine, okay, what do you expect the formula to be? Go ahead. All right, I'm going to close this question in 5, 4, 3, 2, and 1. And then here is, okay, here's the correct answer, okay? So again, how do we do this? We have nitrogen, which has a bonding capacity of 3. We have chlorine, which has a bonding capacity of 1, based on where they are in the periodic table, okay? So I'm going to start with the nitrogen. So nitrogen is going to form 3 bonds, 1, 2, 3, and then that should be bonded with chlorines. So we need 3 chlorines to bind with, or bond with 1 nitrogen. So it should look something like this. So this is how we get NCl3. Okay. So always start with the atom with the higher bonding capacity in the center, and then you can add the other ones around it. All right. Any questions, concerns, comments at the moment? What questions do we have? Anything? All right. Now, here's what we're going to do, okay, for the rest of today's lecture. We can try to explain these common bonding patterns. So to do that, we're going to look into the atom, right? And then we're going to collect some data about the size of the atom and the ionization energies of the atoms to see whether we can get information about why do elements have certain common bonding capacities. That's going to be the goal here for the rest of today's lecture. All right, now let's start with the size of the atom. Okay, so the size of the atom is determined by what? Anybody? Okay, if you compare the atom to a football stadium, the nucleus is like the football in the middle of the football stadium, and the rest of the space is determined by what? What is determining the majority of the space of an atom? Thank you. The electron cloud. Okay, electron cloud takes up most of the space. Okay, in other words, the size of the atom is determined by the size of the electron cloud. Okay, larger electron cloud is corresponding to a larger atom. Small electron cloud is corresponding to a small atom. That's it. All right. Now, with that information, okay, by the way, we get the science information about the atoms from X-ray crystallography. And the way this works is not important. Only thing that matters to us is we get size information from X-ray crystallography. That's all we're going to talk about, X-ray crystallography. Okay. Now, here are some data for you. Okay. And then two questions. What I want you to do is I want you to explain this data. First of all, just make sure that we know what's going on here. A column in the periodic table like this, guys. Okay. This is a column, is called a group. Okay. And then a row in the periodic table like this is called, anybody? Yeah, a period. Okay. So periods goes from left to right, and then columns goes from up to down. Okay. So, or groups go from, up to down. Anyway, so keeping that in mind, I want you to explain the trends you see here. Here we go. You might want a periodic table handy, to answer this question. What do you notice here? I'm only asking what you see here, okay? That's all I'm asking. All right. And here are our responses, okay? So most of us said the atomic radius or the atomic size decreases across the period. Okay, how do we know that? Now let's go back to the data. Okay, now in the first period we have hydrogen and helium. When you go from hydrogen to helium, guess what? The size has decreased because we have the atomic radius on the y-axis here, and then we have the atomic number on the x-axis. From hydrogen to helium, the size has decreased. Again, In the second period, we have lithium. We start with lithium and end with neon. We see that again the size is decreasing. Okay, when you go from lithium to neon. Third period, sodium to argon. Again, the size has decreased when you go across the period from left to right. Okay, so the general pattern is, okay, when you go across the period from left to right, the size of the atom decreases based on the data. Okay, and on the other hand, we are also asked to determine what happens when you go down a group. And if you think about lithium, sodium, potassium, they are in the same group. Okay, when you go from lithium to sodium to potassium, guess what? The size has increased. Okay, and the same thing with this, like helium, neon, argon. Okay, this is the noble gas group. When you go from helium to neon to argon, you see that the size is increasing. Okay, and that's why most of us say the atomic radius increases down a group. All right, do we have any questions, concerns, comments about this? This is just making some observations. Okay, we were given some data. Based on the data, across the period from left to right, the size of the atom decreases, and down a group in the periodic table, the size of the atom increases. Any questions about that? Anything? All right. Now, here's the main deal now, okay? We want to explain this, okay? Now, I'll give you 30 seconds in your groups. Come up with a way to explain this. Go ahead. How would you explain this? And don't be afraid to be a scientist, okay? They use models. Come that again?
Is it Bohr's model?
No, that's for the hydrogen atom, right? Okay. But we're talking about anybody? What model is this? Do you know the name of the model? No? Okay. That's okay. Now, this model is called, we're assuming this. All right. Here's how it goes. Okay. We assume that each period is a shell. Okay. And that is called the shell model of the atom. Okay. So we know, for an example, let's take the second period, which is starting with lithium and ending with neon. Okay. So in the first period, we only have two elements. That means that's the first shell. Okay. And the second period, we go from lithium to neon. That has two shells now. Okay. So the first shell and the second shell. And when you go to the third period, how many shells do we have there? How many? Anybody? First period has one shell. Second period has two shells. The third period has how many shells?
3 shells.
3. Fourth period has how many shells?
4 shells.
4. Fifth period has how many shells? 5, and so forth. Okay. So now here's how it goes. In the second period, meaning second shell, okay, when you go from lithium to neon, the electrons are filled to the same shell. Okay. But the number of protons in the nucleus increases when you go from lithium to neon. Because of that, the positive charge of the nucleus increases. As a result of that, this electron cloud is going to get more strongly attracted to the nucleus because of the greater positive charge when you go from lithium to neon. Okay. Therefore, the size of the atom or the size of the shell decreases across the period. One more time. When you go across the period, the number of protons in the nucleus increases. Okay, that's the first thing you should write. Okay, when you go across the period, the number of protons in the nucleus increases. Okay, and the electrons are filled to the same shell because each period is one shell. Okay, and because you have more protons in the nucleus in the rightmost atoms, you're going to have these electrons more strongly attracted to the nucleus, making the electron cloud smaller. Okay, and that's why the size of the atom decreases across the period. Okay, more protons means higher positive charge. Higher positive charge means strong attractive interactions between the electron cloud and the nucleus. That's the idea there. All right, do we have any questions, concerns, comments? Now, here's the other thing though. Okay. So moving on to the next one. When you go from neon to sodium, neon has 10 electrons, sodium has 11 electrons. Okay. The 11th electron of sodium is not filled to the same shell. It is filled to the next shell, which is larger than the previous shell. Okay. And that's why there's a huge jump in the size of the atom when you go from neon to sodium. Do you see that? So neon is over here and sodium has a huge jump. Why? The 11th electron was filled to a larger shell than the second shell, than the previous one. And that's why the size of the atom increases. Okay, because each added shell is larger than the previous one. Okay. Anyway, what questions, concerns, comments do we have? And that is why when you go down a group, the size of the atom increases because you are adding shells. Each period is a shell which is larger than the previous one. Therefore, the size of the atom increases when you go down the group. Okay, I have 1 more minute at least. Okay, give me a second. Almost there. All right. Anyway, do we have any questions, concerns, comments at the moment? Now, just to summarize what we have talked about, I mean, at least for one shell, can you try this question while I draw something in my notebook on top hat? Okay. I think I know. Yes. I need a new page. Right, I'm going to have size on the y-axis. Now I'm going to have elements going from lithium, beryllium, boron, carbon, nitrogen, oxygen, chlorine, and neon on the x-axis. Okay. I want you to tell me what happens to the size when you go from lithium to neon, okay, across the period. But it's the same thing that you have already answered, actually. All right. So while you're doing this, all right, the general trend is when you go from lithium to neon, the size of the atom decreases. It's not linear, I mean, exactly, but generally it decreases when you go across the period. Okay. This is all I want you to appreciate, I mean, with discussion. Okay. So with that, I'm going to stop right here. We're going to pick this up on Thursday. All right. Bye, everybody.